Should start from here. You might have seen this in Module 5. This is called cobalt 2 chloride. If you remember that, okay, we put that in some water, dehydrate the heat, okay, and you see the color change from this kind of blue, purplish, kind of pinkish color to the blue. So let's describe what's going on in here. This is giving you some cobalt 2 chloride in terms of the solid state. Okay, so let's give you some example here. So we have a cobalt 2, CO2 chloride, Cl2 solid. Now, as I am adding some water here, this comes in solid state. Let's put some water in here. I'm making this to be now called a hydrated. Do you remember the term called the hydrated salt? Hydrated salt, okay, something we learned, and it's showing you the colors of this. Yep, it shows the kind of purplish, red kind of colors, pink colors too. So, writing down as a form that the cobalt chloride is now divided into these. We added some water into it. Now becoming into cobalt, that's a 2 plus aqueous, and leaving that 2 chloride aqueous form too. Yep, that's something we discussed about the dissociation of the ionic compound in the water. So let's have a think about what happened to the cobalt inside that too. We described the cobalt is now hydrated. Hydrated cobalt. Cobalt 2. So what actually showed it is this. We have a cobalt in the middle with the 2 plus charges. Do you remember the water has some partial charges of the positive, negative, and positive too. So each of the cobalt in this case can attain that up to 6 water molecules nearby, which means there will be water molecules comes along, 1, 2, 3, 4, 5, and 6 like this, and hydrogens, of course, showing the forms of that. Now, in the case of that there will be interaction of those partial negative charges of oxygen to the cobalt given over here like that. We call this as a hydrated cobalt, as we learned as well, and we know that this interaction between these is ionic ion dipole interactions now form too. But if you look at that, cobalt itself doesn't really lose its 2 plus charge. It still having the 2 plus charge inside. So in a case we have something that have a metal in the middle, having more like a water is kind of contained, like I showed me the 6 water is kind of attracted. This is called a complex ion. So complex ion is another terminology that we're using to describe the hydrated salt or hydrated cations in this case. For the complex ions, as you can see that we have the central metal inside called a central metal. And these central metals are generally be transition metals. For this complexation process, I will make a separate video. I'm making this video separately and put it onto the YouTube because this is something that's very important, something that will confuse you a lot of times. But if you understand that, hey, we have a hydrated cobalt, by mixing that simply, I'm adding some water into it. Water's molecules kind of surrounded that to making form the complex ion. That's it. Okay, that's all you need to understand for now. So, and what we have outside of here is these are called the ligands. All that. So you may think about, this is basically all kind of tails. You think about 6 of the tails kind of contained attached to the cobalt given over here too. In the forms of the metal ions, we have the ligands. We call the complex cations, or complex ion in short. So in a way we can describe the complex ions. We may describe that as, hey, we have a metal, have some charges plus, with the some aqueous. When this is combined with the n number of the ligands, which is aqueous or the liquid, they will form the complex metal structure called the M and Ln of the plus charge. These are complex ion structures. So for example, we have a cobalt 2 plus aqueous given, combining with 6 of the H2O liquid. Okay, giving you that cobalt with the 6 H2O, so we have a 6 of those, H2O 6, look like this, and carrying the charge of 2 plus on the top. In a way of describing that in chemical formula, this is what actually happened of the cobalt 2 plus AQ is. But sometimes we don't really want to write that all the time. This is why we simplified it to the cobalt 2 plus AQs many times too. But that is what's actually happening in terms of the hydrated salt or the complex ion structures. Okay? And as you can see that, the cobalt has a very specific, clear and distinctive colors, which is showing the colors of the reddish purple. Which means whenever you have a colored solutions, they're all more likely forming the complex ion structures. Another example is iron. Iron 3 plus, aqueous here like this too. Can you see that? Iron 3 plus solutions. Okay, means it shows the very clear color of the orangish, yellow color, brown color too. It means that this is the kind of distinctive color, the signature color of the iron 3 plus as well. This happened because they combine with the 6 water as well, the liquid, forming that into Fe comes in and the H2O have the 6 of those all together, now becoming into leaving the 3 plus charge. And I call this is basically complex ion, but also be a hydrated ion. Similar things happen to the copper 2 plus with the 6 H2O liquid. They're always forming into these copper, they H2O, there are 6 of those, and leaving the charge of 2 plus. Now, as you can see from the colors of the copper solutions, they're generally showing the colors of this, the blue color. This is a hydrated salt, hydrated copper inside there too. But in a way of the systematic name given them to, we actually given some number of the water as the using that numbers. So this is actually known as cobalt 2 hexahydrate. Now, hexa stands for 6. Cobalt 2 stands for cobalt 2. Hydrate stands for the water. That's it. So whenever we have something hexahydrate, means that we have 6 water molecules attached to that. And this is the reason why, if you remember then in module 5, we have a formula in the cobalt 6 hydrogen water into that too. And that's because it's showing you that the structure of this. The name of this is then iron 3 hexahydrate. Now, this is copper 2 hexahydrate. It's kind of systematic name, but it's sometimes known as hexahydrate cuprate, which is another name of the copper as well too. But don't worry, you don't have to memorize all of that. What you need to know for the HSC and the trial is you need to know how to draw the structure of those complex ion. Okay. You also need to know the chemical formula of them forming their complex ion too, but mainly dealing with the water. And for most of the metals, they always comes with the 6 waters all together, just the 6 waters. So it's showing you on the table over here. Page, what's the page number here? Page 21. It shows you that all the hydrated ions of the iron 2 plus 3 plus, 2 plus 3 plus, cobalt 2 plus, copper, nickel, aluminum, and chromium here. If you can see that, there always comes with the 6 of the waters too. Okay. Now, probably if you make the exams making the question harder, they may give you some of the ammonia into it. That's it. You won't get any of those hydroxide over here. All right. Does it kind of make sense? So all you need to memorize hydrated salt, which is basically having the 6 water and making the hexahydrate formations. And you had that one question in your practice question last week. It's called the hexahydrate or something. That's what I mean by the hexahydrate. And that's what the complex ion forms. All right. Then let's have a think about what happened between here. We have then cobalt water. So as you can see that this is basically telling you I have this. Can you tell? Okay, I have a cobalt which is hydrated here. What if I add some hydroxide into it? Let's have a look at the reaction between this. So I'm going to add some sodium hydroxide into cobalt 2 chloride solution here again. So see what happened. It changed the colors. Can you see that? used to be blue and sorry, gone red, now being turning to purple blue. We kind of discussed that this is probably changing the pH, according to Le Chatelier's principles, making a shift to the left-hand and right-hand side, turning the colors back into. Which means if I add some acid into it, I don't have acid here, but it turns back to the colors of the pink as well too. But you can actually see that there's a bit of like a chunky, like a precipitate is formed too. This is the cobalt hydroxide precipitate form inside. So what actually happened between them is, rewriting that here, started from that, we have a given cobalt and H2O6 hydrated over here. So it look like this. We have a cobalt inside, CO2 plus, with the 6 water molecules. That is what they look like. And next, making the 2 plus charges hold together like this. Okay. Also, you can look at the, it's a better diagram here. The page 16 is kind of giving you that kind of diagram too. Okay. Now, this is reacting with some sodium hydroxide into it. Then what they do is, hydroxide will take a place of the water. Okay. Considering that hydroxide will take a place and then they're forming the solid state, what you can tell is there were 2 plus and that times 2 of that. So what they do, this is actually comes negatively charged, which means that cobalt will be now attached to that. So they will attach with the hydroxide, 2 of those, negatively charged, becoming look like this. We have a cobalt in the middles, still be in the middles. There will be a water molecules kind of surrounded by this, a bit of that. But there will be a place for the hydroxide, taking a place of the water. Becoming into that, now becoming into cobalt hydroxide, which is a solid forms here like this. That's basically what happened inside of this reaction. As you can see, like it started forming the precipitate. Can you see that? Kind of murky, you see the precipitate formed. This is basically what happened when you add some hydroxide into that cobalt chloride solution. Okay, again, the reason why I'm bringing this cobalt chloride again is this can be mixed use with the module 5 content that we learned, the equilibrium in Le Chatelier's principle back into it again. But again, important to remember that complex ion is nothing special about just simply hydrated salt form, hydrated metal cations. And as we can tell that, this is telling you the very specific colors of that cation metals. So again, complex ion is only for the metal cations, nothing for the anions, and only for the cations, especially the transition metals. So by using that terminologies, we are able to construct another flow chart using that, which is given on the page 22. Look like this. In a case where we have the unknown cations, we can test one. We can add some hydrochloric acid. Now, what we know about hydrochloric acid, chloride to those cations, chloride will only form the precipitate with lead and the silver, that two only. Then, if we get the white precipitate is formed, we know that that must be either be silver or the lead. Then what you do in the second, the confirmation test is we're adding some diluted ammonia into it. Now, silver and the lead is both in the transition metal, which means that they will go through some complexation reaction with the ammonia. And for that reaction, you don't have to memorize that, but it's good to know the ammonia with the lead. We're not giving the lead here. Don't worry about the lead here. They will form the white precipitate with the ammonia. Okay, and the silver form the brown precipitate with the ammonia too. Okay, so they're going to form some sort of precipitation reaction as well. Sometimes they form the precipitate when the complex ion form, sometimes they don't. So this is an example of they form the solid with a precipitate complex ion. And this is not hexahydrate. Does that make sense? Okay. So that's not too hard. Complexation looks really complicated because it looks like, wow, what is going on? But the actual question you get in the HSC, we never had a really complicated question about the complexation because the concept itself requires the high level of the chemistry. That we actually need to talk about a lot of orbitals, which is not required knowledge for year 11 and 12 high school levels. So let me show you one question that related to that that we had before in the practice questions. Look like this. Cobalt 2 ions can form the complex ions with the 4 chloride ions there. So what is the chemical formula and the charge of this complex ion? This is it. This is something that you will get a lot of times. So how do we do this? We got to determine that which is your ligand and which is your the central ion. So central ion is cobalt 2 ions inside. So let's draw that. We have a cobalt inside 2+. Okay? This gets surrounded by actually the complex with the chloride ions. So how many? We have 4 of the chloride ions, Cl- there. Then what do you expect for these? This is making some complex ion forms, yes, but think about the charges of that. You have a 2+ inside and 4- is outside, look like the ligands having a 4- too. So we can tell, the total charge of that would then simply becomes 2 minus of this. In way of the chemical reaction form, you can write it here like this. Cobalt 2+ aqueous reacting with the 4Cl- the aqueous forms. And in forms of the complex ion, you got to write it as CO, the Cl4, and bracket 2- like that. It's not just a COCl2, it's called the cobalt 2 chloride, actual forms of the complex hydrated ion forms too. Does it kind of make sense? Okay, it's not so complicated. It's all about the relation between the central metal ion and the ligands. Showing another question. Okay, try this. Use the complex ion shown to answer the following questions. So, what is a metal ion in the complex? What's the ligand? Explain why the ligand is orientated that way. It is shown in the diagram. So, answer the A and B and C. I'll give you about 2 minutes to answer these questions for now. It's actually just no bracket. COCl4 would be actually the right answer for the previous one. I just put the bracket for the H2O because that's kind of complex ion forms. So remember that the water doesn't really carry any charge. Like technically it doesn't have any charge. It only has the partial charges. So you can imagine that ion, which is having positively charged, we're attracting those partial negative charge with oxygens, making forms of the hydrated iron 3 ions, or complex ion forms. So A, what is the metal ion in this complex? As you can see that we have iron, it's central metal, the complex in the central metal that we have, but falling to the charge of the complex ion 3+. And knowing that the water doesn't really carry any charges means that it'll be 3+ altogether, just ion 3+. Okay, in other words, this is showing you this stage of this one, ion 3 hydrated salt. Okay, and as you can see, like the colors of that is clearly kind of brownish or the yellowish brown or kind of orange brown, whatever you call it. What about the ligands? What ligands are attached in here? We can see the ligands attached is just simply water, called the hydrated. So how many we have? We have 1, 2, 3, 4, 5, 6 again. So hexahydrated forms of that ion complex. C. Why do we have that? Why are we having this? We can see like they're metal ions because of the interaction between metal ion and the dipole of those water. So we call what? This is called the, due to those oxygen atoms through the lone pairs forms. It's actually forming due to the ion dipole interaction or dipole bondings between them, where the metals are, the metal ion is positively charged, and the ligand, or the H2O, has the partial negative charge on the oxygens. Therefore, due to the interaction between that, it's actually called lone pair of that interactions. So what they actually do is the water molecule has a structure look like this. You can remember the Lewis dot structure or Lewis structures. Water look like that over here. This is kind of forming some sort of the interaction. The negative charges in lone pairs are interacting towards to that given ion 3+. Remembering that electrons are negatively charged and ion 3+ are 3+ charges too, so there will be interaction between the electron towards that. But again, you don't have to know. Okay, and just give me some explanation to give you some, so they can imagine about what's actually happening between the water molecule to the ion 3+ charges. But that's all you need to know for the complex ion forms. Okay, we didn't have any like harder questions about complex ions. This later on will be mixed use with the colorimetry, because colorimetry simply means that all those color solutions have the specific colors. Now, give me some ideas here. Why is that colors of the yellow or colors of the orange? Anyone? Does anyone know why can we visually see the colors of the orange here? The light reflects means that all different type of light, which is like a kind of other colors, get absorbed by that, except the orange color. So only the orange color get reflected. So your eyes are capturing the reflected and the light, which is the orange. Same for the blue color of the copper too. That's showing you this kind of blue, means that all other colors get absorbed except the blue. So you only see the blue color reflected. Little bit of the physics, but this is also get used in the spectroscopy next week, and this is only used for the colored solution too. I can't use that for the solution of the silver chloride, which is kind of the clear colorless, because they do not have the colors. Having no color means what? They're absorbing everything. Or like a black colors, they're absorbing everything too. Or they're not absorbing anything. Colorless means they're not absorbing anything. They just go transparent, penetrating through the light as well too. That's a bit of like, some common science knowledge you need to have to understand colorimetry next week, but also related to the complex ion forms too. Okay, so complex ion is another method, the qualitative method to figure out the presence of the cation again too. Any questions about complex ion forms? Nothing really serious, but it's more going to deal with the precipitation reaction a lot of times.